chocks?
I need chalk, yes. Oh, here it is. This is what I have.
No, you have plenty of there.
There's plenty here, okay.
You have color chalks?
No, well, I like white. This is white? Yes, I'll
yeah,
just...
I think but this...
This is better?
Supposed to be...
I'll use these. Let's check.
Hi, I'm the chairman.
Hello. Okay. Hello, Eric.
I will tell you when it's 30 minutes to the end.
Okay.
In 10 minutes.
Okay. All right. You left some notes here. No, I have 3, I think, and a colloquium.
Yeah, 3 plus 1.
Okay. So you remember in my opening talk, I told you, I said that space and time are emergent concepts, as is gravity. Most string theorists sort of believe that, but if asked to explain what that means, they don't really have an idea. They have some examples, partial examples, but no true idea of the big setting in which space and time wouldn't be primary concepts, nor gravity, the dynamics of space and time. Erik Verlinde has been, over the last year, trying to imagine such a larger setting in which space and time and gravity are emergent. And in a series of unpublished papers, correct? Nothing's been published?
Nothing has been published.
In a series of unrefereed papers in the experimental world known as rumors. And we're lucky to have the opportunity to hear him give 4.5 hours, which is roughly 5 times the normal length of his exposition of this set of ideas, to us in a series of 3 lectures called Emergent Gravity. And being a school, questions from the audience, including professors, not only students, are encouraged. And I think this could be very exciting. So without further ado, Erik Verlinde from University of Amsterdam and KITP soon.
That's good. All right.
Emergent Gravity.
Thank you very much, David. I mean, indeed, well, I hope to tell you about these ideas about gravity. So gravity, as David said, has many indications of being emergent. And what do we mean by something that is emergent? It means it is derived from something else. And And it's important that I write here something. Because, well, first of all, what does it mean if gravity is emergent? It means that the laws of gravity as we have now, we use Einstein's equations, and we use ways of describing space-time in terms of curved space-time to describe gravity. So gravity is closely related to space-time. So if gravity is derived from something else, then also space-time has to be viewed in a new way. So there's something that gives rise to not only gravity, but you have to think about even space-time as being then emergent. And as you know, gravity is closely related also to inertia. I mean, if you think about the equivalence principle, there's a direct relationship between the inertial force and the gravitational force. So mass, how things move, but the whole concept even of matter and forces is something that we generally take for granted. And our view of the world, and actually our current paradigm, is very much based on these concepts: gravity, space-time, matter, and forces. I'm going to think about emergent gravity, but I also have to then think about what space-time is, indeed, and how matter and forces arise. And there's something that gives rise to it. So this is what I call emergence. I think emergence also means that we ourselves use concepts that generally are derived from something else, and therefore we should think about a language in which these things can be defined. Now, there's another way of thinking about this, namely, if gravity is emergent, it also means that the equations that we use for describing cosmology must be emergent. I mean, general relativity is our current paradigm for describing the expansion of the universe and everything that evolves in it. And actually, the usual paradigm is actually that we believe that the universe sort of started somewhere, and that all of these concepts, space, time, matter, and forces, arose from some big bang. And actually, the paradigm right now seems to be we start from nothing. And then we let it explode, and that gives rise to space, time, matter, and forces. And I think this is a different way of thinking about it. There's something that started, and where we should think about where space-time arises from. And we'll see, I'm going to actually fill in this something using ideas from string theory and from black hole physics. There are different ways you can think about gravity than in the usual way. So this big picture, I think, doesn't really make sense. There's nothing like something that starts from nothing. So emergence has to do also with how the universe sort of started. Or better said, how we should view cosmology. Because cosmology has big problems. I mean, there are many things that we don't understand about cosmology. And this is where I will eventually go to. I mean, you may think that talking about emergent gravity is some theoretical philosophy thinking about what space-time is, and that only sort of tells us about the very small. There are many things in cosmology, and if we look out in the universe, that we don't understand. There are things like dark energy, and dark matter. And most people try to understand these quantities in terms of this old paradigm, the old concept. In particular, dark energy will be represented usually by just one constant, while it represents more than 70% of the energy of the universe. And dark matter, we don't even know exactly what it is, and we have seen all evidence that there is dark matter, but there are many ways in which it's still a very mysterious part of our view of the world. And this is more than 96% of the energy in the universe. And if we don't understand so much of our universe, it's clear that we may be using even a wrong paradigm. So at the end of the lectures, I will go into particularly dark matter. I mean, I will show that the ideas that have to do with emergent gravity will teach us about dark matter. And I will present really even comparisons to data. I mean, I want to not just think about theory, which will be sort of on this side. So the theories I'm going to think about is, well, string theory. It's certainly one of the most important clues about what emergent gravity will be. We have ideas there. We have indeed examples, like David said. I mean, we have examples like ADS-CFT or other ways in which we can think about open and closed strings. Now, I'll explain more about that. For me, these examples will be ways of extracting more general principles, because eventually I want to go to data. I mean, there are data on this side, observations. And in order to go from this idea on the theoretical side to the observations, we need to sort of move away from the more abstract language to something that we can compare to the actual data. So I'll put something in the middle. And as I already said it, I mean, what I'm going to do is look indeed at examples, but I'm going to talk about certain principles that I'm going to use and extract from the examples. And these principles actually will allow me to, well, say general things about how indeed gravity can emerge, what it means when a force is emergent, and also what it means if space-time is emergent. And then we're going to have some ideas which we can eventually compare to data. So these lectures will consist of several parts, of course. I mean, I already said there was examples on the theory side. I'm going to talk about these principles. Actually, we're going to do this in the first lecture. The string theory side I will reserve for mostly the second lecture. That will be quite explicit about even what we can put here, what kind of systems you can expect we can derive gravity from. And then the third lecture, I will indeed talk about the dark matter. And actually, probably at the end of this lecture, if I have time, I already start telling you a little bit about dark matter, because it's not something that many people are very familiar with, in particular not the observations. Because there are many issues there, and even problems that people don't really understand about the universe. I mean, the fact that I say here is dark energy and dark matter is only part of the problem. There's also problems like that people don't even know where all of the baryons are sitting. The usual matter, which we think of as representing 4%, if we start looking locally in our neighborhood, in our universe, we can't find it. We don't see the 4%. So these are things that actually need to be explained, and also there will be relationships between these facts and the data and the theory. So let me now come to the idea, what are the principles I'm going to look at? So one of the biggest hints that gravity is emergent is that it knows about entropy. It knows about the entropy of the microscopic description of whatever it is. I mean, we believe that if we look at the horizon area of a black hole, that we are really counting the entropy of the microscopic states. How does gravity, and why does gravity know about the number of states at the microscopic level? That's a miracle. I mean, there's a classical solution whose horizon area somehow captures the number of states of a microscopic system. There must be a reason for that. I mean, if I write down the Boltzmann's equation, or let me write it as omega. So Boltzmann wrote down this equation, and he actually had a quantity which was entropy in thermodynamics and related to something microscopic, namely either the volume of phase space or the number of states. I will actually use both languages. I mean, we can think about the world as quantum mechanical, and then we should be counting states. But we can also think about them as derived from some variables, and then those variables have certain set of classical solutions, and the space of classical solutions is what describes the phase space. And then what we mean by entropy is just counting the volume of phase space, because you know that semi-classically the volume of phase space is related to the number of states. But this is a microscopic description, and this is macroscopic. And I think no one would disagree that thermodynamics, or, well, through statistical mechanics, is actually an emergent description of macroscopic phenomena, and that microscopically we know basically how it arises. So for me, thermodynamics is the perfect example of a set of equations that we know how to derive from an underlying description. And actually gravity has many links with it, and this is, we would like to know why. Another thing that is closely related to gravity, and that's we've seen in examples like ADS-CFT, is the renormalization group. there's ways in which in ADS-CFT the gravity equations can be thought of as renormalization group equations, and then it makes clear that there's some connection between, well, what we do in renormalization, namely integrate out degrees of freedom, and the way that gravity emerges. And both of these give rise to the idea that gravity is a consequence of integrating out degrees of freedom at a microscopic scale. Now, what about quantum field theory? I mean, we can think about many things in the world in terms of quantum field theory. But for me, quantum field theory is clearly also an example of an emergent framework. It's a general framework. Because what I want to explain is that gravity must be thought of as being a universal phenomena. It's something that should not depend on the precise microscopic details of the stuff that we integrate out. I mean, it has only one constant, well, Newton's constant, and maybe two if you add the cosmological constant, but it doesn't have many other parameters, and so these parameters somehow must capture something of the microscopics. Well, in quantum field theory, we have many more parameters generally, because we can write down quantum field theories with many more couplings. But we know that the ones that we really can use in describing forces generally have only a few couplings. And we know why that's true. Namely, if you think about a microscopic starting point where we think about the world, say, as a lattice or something like that, we know that we can arrive at quantum field theories by going through a sequence of steps which are related to the renormalization group. You think about a system, if you think about microscopic world as some lattice with some degrees of freedom on it, those degrees of freedom can enter the Hamiltonian, and I can think about, for instance, spins, but there can be other type of degrees of freedom. And then in here there may be certain coupling constants which enter into the Hamiltonian. And then the idea is to get to a quantum field theory is that we have a lattice spacing which I can call A, and then I go through renormalization group steps where I make the lattice spaces bigger, and then I integrate out certain degrees of freedom. I mean, I'm sure you've all seen this, and then you get some new Hamiltonian with new degrees of freedom where you sort of omitted part of this. So this involves coarse graining. And then you get some new set of coupling constants. And this defines a renormalization group. And instead of the lattice spacing, I can think about an energy scale, which is sort of like roughly like 1 over the lattice spacing. And then at low enough energy, I can think about only of long wavelength kind of changes in this. And you will replace those variables on the links or on the sides by fields. And eventually you enter into a field theory description if you can take the continuum limit. And this is how you end up with some picture of the field of quantum field theories labeled by coupling constants. And then you have the renormalization group equations that tell you how these coupling constants depend on the scale. And there are some beta functions that enter in here. So you have a flow of in a very big space, because a priori, certainly if you have still a lattice, there are many, many couplings you can define. But eventually you know that only a small set will survive. And in particular, when we go to the fixed points of these renormalization group flows, where the beta functions are vanishing, we end up in a very special situation where many of these couplings have disappeared. But we always flow from the UV to the IR, and that means we always integrate out degrees of freedom, and we forget about certain microscopic details. So then we can separate the coupling constants depending on the scaling dimensions of operators. So coupling constants are related to operators OI, and these have scaling dimensions delta I. And then you have to separate the ones that either can be, well, you can have them either with dimensions larger than the dimension of your space or equal or smaller. And we call these the irrelevant ones because they will be not relevant at low energies. These are the marginal ones, and these are the few relevant ones. But what I want to indicate with this is that we understand why quantum field theory is a very good description at low energy, basically from a starting point that's not even that well defined. I mean, it's not something that I can make very precise, because there are many, many starting points that all flow to the same kind of low energy description. So quantum field theory is universal, and it's universal because of some attractor kind of mechanism, in the sense you can forget about many couplings. But most quantum field theories actually, and this is the way you should think about quantum field theory, are effective. I mean, they're actually the way we understand why quantum field theory enters in nature is because we can always define quantum field theories with a cutoff, and then they're effective quantum field theories. And to me, this is the only way that we should view quantum field theory, even though there are some very well-defined quantum field theories, in particular the ones where the beta functions vanish. Because then you enter into what's called a conformal field theory, where you have much fewer parameters, as I said, but it's also a very well-defined theory. It's even UV complete. And this may say, well, this is somewhat surprising, because the way you enter into a conformal field theory is by integrating out stuff and then going to a fixed point. But at the fixed point, you basically don't see any remnant anymore of the fact that you introduce the cutoff, because everything is scale invariant, and you can take the cutoff again to zero. I mean, if you think about the energy scale, but you can also take it back to infinity. I mean, or the cutoff scale A, you can also, I mean, there's no difference, I should say, between the UV and the IR if you are in a conformal field theory. So it's actually UV complete. And so it's actually very well defined, I would say, mathematically. And it's even quite beautiful in the sense that it has all kinds of symmetries, generally, like in 2 dimensions it has a Virasoro algebra. But we know it doesn't describe nature. And actually, indeed, we can think about it as some limit of some much more general framework, which is quantum field theory. But I would indeed say it's very unnatural. Actually, highly unnatural, I would almost say. Physically. By this I mean, if you take a CFT defined all the way in the UV. So if I think about the world as a continuum conformal field theory, which mathematically is very nice, I do something physically very unnatural, because conformal field theories are fixed points in the renormalization group in the IR. Nevertheless, they look very beautiful, and you might believe that the world is described by this, because indeed n equals 4 Yang-Mills, for instance, is a conformal field theory, and it looks very beautiful. But it's not at all like the world, because if the world would be a conformal field theory, there would be no gravity. So for me, the proof that it is not a conformal field theory is actually that there is gravity. I haven't said anything about strength.
Can you elaborate on what do you mean by n equals 4? Which is it's actually dual theory.
Well, I will explain that, why it's the case.
But there is gravity.
It's not, no, the fact that n equals 4 Yang-Mills is defined in a space-time without gravity has to do with the fact that it's a UV complete theory, in the sense that I can take a continuum limit. And gravity will actually only appear when you accept the fact that there's fundamentally cut off, or at least that there is a finite number of degrees of freedom, first of all, and that there are indeed it's not possible to take a continuum limit.
It's just, yeah, when you say there's no gravity, you have to define space.
It's the space in which the conformal field theory lives. So it doesn't couple to gravity. And actually, I'll explain how that arises. Because I haven't said anything about string theory yet. But I'm afraid the same thing applies to string theory. And I'm going to explain that.
Now, there are conformal gravitation theory, which most of us think are sick, but you can write it down.
So this story is about quantum field theory, and it's not about gravity. I don't think that gravity can be put into the realization group framework, and it should not be tried even to think about gravity as a field theory, quantum field theory. So there are examples of people that, well, first of all, there are other quantum field theories which you call asymptotically safe. That means that there are only conformal field theory in the UV. And some people think that gravity may be quantized by thinking of it as a quantum field theory, but then maybe in the UV it's conformal field theory. This to me is totally illogical, and actually the explanation or the logic of how gravity arises will make clear why that's the case. I think this story is not complete. It's not finished yet, because there are certain assumptions made in getting to quantum field theory, especially about the decoupling of the things that I integrate out and the things that I'm left over with. So you integrate out shells if you do of momenta, or you integrate out degrees of freedom, and you assume that at low enough energy, there's no effect except of adjusting the coupling constant. This is generally not true, and gravity will be a consequence of the fact that I have to keep count in some way of what I'm integrating out. There's an improvement on the Wilsonian realization group flow, which will have to include gravity. Because how does gravity arise? We'll see how this happens in string theory. I mean, here are coupling constants, and coupling constants, they couple to every operator in the theory. And one of the operators in the theory is the stress energy tensor. And so there will be actually a metric sort of playing the role of a coupling constant. So what I'm going to tell you, if I want to improve on this idea of realization group flow, where I want to keep track of degrees of freedom that I've integrated out, there's a way of doing that, namely by including coupling constants which themselves become dynamical. And if the metric becomes dynamical, I have something that's called emergent gravity. And this is actually the way that string theory works, and I'll explain that in a minute. So yeah, all right, this is just a starting point for a quantum field theory, but I want to go to gravity. Did I have something left here? Yes. So I say string theory is something similar because indeed, I mean, we know there's already an example of string theory, which is indeed ADS-CFT, which is basically the statement that there is a quantum field theory, namely CFT, which is equivalent to a string theory. And that string theory has gravity in it. So what does it say here? I mean, in string theory, we have generally the idea that gravity is automatically included in it. If we have open strings and we have closed strings, then immediately we have gravity as part of the excitations of the closed string. So I have to explain how we can think about emergent gravity from a string perspective. So let me now go to string theory and actually also see how we can think about ADS-CFT from that perspective. So in string theory, as I said, we have closed strings and we have open strings, and we also have d-branes. And we can think about the closed strings as being associated with d-branes quite generally. I mean, if it's just an open string, we can also have space-filling d-branes. So this is the picture of string theory where gravity is in the closed string sector. The fact that it's in the closed string sector already tells us that it's something else than what the open strings are describing. And for me, the open string is much more what we can associate with quantum field theory. So this story about quantum field theory you can take as a description of what's going on the d-brane in terms of the open strings. The closed strings are indeed like the coupling constants of the open strings. And that's one way we can view string theory. So the closed strings are also in this story, but they describe the coupling constants, which in quantum field theory are constant, but in string theory they're dynamical. Now, a very important calculation that basically every time appears when something spectacular happens in string theory is the fact that there's an equivalence between an open string diagram, which is a one-loop diagram, and a closed string exchange. Of course, it's the way that Polchinski also sort of calculated the force between two d-branes. Not sure how to draw this clearly, but anyhow, there's the two d-branes, and then there's an open string one-loop diagram that exchanges. And another way of viewing this same diagram is as a closed string exchange. This is an important fact. I mean, it's a quantum effect in the open string, namely it's a one-loop amplitude, but in the closed string it's a classical effect. So we're relating here something which is quantum from the open string perspective to something classical in the closed string perspective. And to me, it's already an indication that we cannot think about the closed strings as being truly fundamental.
Well, we know this from 40 years ago. That's how closed strings were discovered.
As some crossing in, I know.
As singular open string intervals. And they're contained in open string field theory.
Yes, but I think then, all right, yes, fine. But what I will say, because, okay. In most string theories, we are not able to decouple the closed string from the open string. And this is why in string theory, gravity is almost inevitable. I mean, otherwise we would have string theories which don't have gravity. So there's a way in which closed strings propagate, but we have indeed other ways of viewing it, namely in terms of an open string one-loop amplitude. And there's actually a parameter that you can choose in describing what string theory is. Because if I look at this diagram, I have this option of describing it one or the other way. And as I will make clear, this is also one way of understanding what ADS-CFT is. Because I should tell you, the first time that Maldacena proposed ADS-CFT, I was confused about what he derived. Namely, ADS-CFT is basically derived from such a picture from d-branes, multiple d-branes, and taking some kind of limit, a low energy limit, where you try to decouple the open strings from the closed strings. So on one side, he decouples the closed strings from the open strings, and then he derives from the basically the quantum field theory that describes the open strings, you can get to the conformal field theory, because you decouple it. And basically the limit that I've been taking here to the fixed point set is the same limit that he's been taking in the low energy limit. You arrive at the CFT side. But then he goes to another story where you look at the back reaction due to the closed strings, and you find some open closed string theory in an ADS background that contains gravity. Now the reason I got confused is that this is some limit from something we call string theory. If you take a limit of one object, which we call string theory, and we end up with two formulations, namely one closed string formulation and one open string formulation, I get confused, because how can you get two objects by taking the limit of one? If you take a limit, you never get two objects. You can make two objects to make one, but it's not like you can make...
If you had a dual invariant formulation, say, of gauge theories with electromagnetic duality, which you don't, just like you don't have a general formulation of string theory, then you would have a situation where in two limits you'd have a theory of electrical monopoles and a theory of magnetic monopoles.
There are two limits, but here's one limit which produces two formulations of a theory. What I'm claiming is that string theory itself has already many formulations. And this is related to the picture I draw here, namely, there is a choice I make whether I describe something in terms of open strings or closed strings. If I look at the closed string propagator, or I view this as an open string one-loop amplitude, then there's a moment when I think about this. Well, this is clearly, you would say, a one-loop amplitude in open strings, while this, if I make it even longer, should clearly be a propagator in closed strings. But there's one moment somewhere where I have to decide whether I call this a closed string or an open string.
But you need the brains.
In order to understand this, we need brains, and I'll make clear why it's for me allowed eventually to think about the brain picture. Because I think, first of all, this is a perturbative strings, what I'm doing here. And we know that eventually we also have to understand what string theory is itself. So we may think we know what string theory is, we only know it from a perturbative limit, and we want to know eventually more where it comes from. And then this is an important element. But somewhere in a diagram, I can always choose to think about that diagram from an open or a closed string perspective. It's interesting actually to do this calculation and sort of go back to the calculation that Polchinski did. I now remember what I forgot, by the way, but hey, I'll go back to that later. Let me write down the expression for this diagram in, so there's a certain amplitude for a diagram of this sort, namely you sum over all states that are propagating around a loop. I can actually write a similar expression for the propagator in the closed string channel, but let me do it in the open string channel, because then I'm summing over all states. And so what I'm doing here, I'm thinking about indeed 2D brains, and they have a certain separation, which I call x. Then you sum over all states, and then what we do, we introduce some swinger type parameter, which is the length of the tube. So I'm going to fix this length to be, say, 2 pi or something like that. Then I have a parameter which I call s, which is the swinger parameter, which measures the length of the cycle in that direction. And this is then multiplying something like p squared plus mi squared. But then, because there's the length of the string, there's also an expression depending on x squared, which is measured in terms of string units. Let me just not write the string units in here. So the string units I put equal to 1. And then we sum, and actually it depends on boundary conditions, but generally we like to sum with some possibly a -1 to the f in here. And of course we count all the states with a certain mass, so maybe there's some degeneracies that I put. And then I integrate over s. And you integrate from basically 0 to infinity. But this is precisely where you integrate over all shapes from this to this. And so there's some way in which I can make a distinction between whether I call it an open or a closed string. Because maybe if I think about indeed putting a short distance cutoff on the open string channel, that means like introducing an epsilon here where I don't integrate all the way to 0. That means that I don't allow this width to be smaller than epsilon. Then I left out a certain part of this integration. It's that part which I can then represent by the closed strings, which are propagating, well, because I still have to include then this diagram, but then this you can add as a closed string diagram. So one thing we learn is that closed strings, classical, because this is a classical propagator, they basically are equivalent. So I should say at long distance, because if I say that the epsilon, for instance, is very small, it means basically this propagator is very long. So classical closed strings in the IR are equivalent to the UV, basically the quantum properties of open strings in the UV. This is what we call the UV-IR correspondence. It's the fact that the long distance property in gravity is a consequence of the short distance properties of of open strings. Here we also have to integrate over these momenta, by the way, which are the momenta along the d-brane, while the x measures sort of the transverse distances. Let me go to a particular example, namely where I think about these d-branes as d0 branes. That means they don't have any extent in space, but they're really point-like objects. Then I still have here an integral to do over the time-like direction, because there's still an energy along the brane. Now, the following thing I will leave as an exercise, namely, if you do the integral over S, I think there is actually an integral here. It's ds over S, and the reason is that if you think about this amplitude, this will actually produce the logarithm of this expression, and we're indeed computing the logarithm of some determinant. But if you now do the integral over P0, you get some power of S just from the Gaussian integral, and then you can scale out the expression in here, and you find that the amplitude is basically the sum over I of something like the square root of mi squared plus xi squared, of x squared, with -1 to the f and then some degeneracies. Simply because, well, you can just see it from the scaling from the s to the power a half. But this also tells you this is like the 0-point energies of a bunch of oscillators. You can think about the open strings as just oscillators with a certain spectrum of masses. And this is the amplitude, at least between these two d-branes. Now, the following thing you can do is, namely, how can we now get gravity out of this? And this is the calculation that Polchinski basically did. One thing we see is that if you look at this 0-point energy, that if you would look at one of those states, it would actually grow as a function of the distance. While we know that the force that we want to get is something like a 1 over x potential if it would be gravity in 4 dimensions, and it may be higher amplitude, 1 over x to some higher power if we want to have gravity in higher dimensions. And the reason has to do indeed with this sum over I, namely there can be cancellations, and particular supersymmetry is important in order to see an emergent gravity. So this is an example of an emergent gravity because it's interpreting the gravitational force between those two d-branes basically as a result of 0-point energies of a bunch of oscillators whose frequencies depend on the mutual position of these d-branes. And let me just do the first example. Let me expand this, namely, I put out x, and then you get some expression which is some power series in mi squareds over x squareds to some power n with some numbers here which depend, but there are still -1 to the f and some di's. And the numbers here are just combinatorial numbers in expanding the square root. Now, if I assume that the first term, so there's also sum over n. So the n equals 0 term would indeed be linear in x. But so the n equals 0 term just would cancel if there's an equal number of bosons and fermions. Because then this is just constant, 1. So is there an equal number of bosons and fermions, the first term would cancel. And then if you write down the next term, then you would go like something like sum over mi squared -1 to the f di, and then it goes like 1 over x. If you have more of these terms vanishing because of supersymmetry, which has actually happened in the superstring, then the powers of x would become even higher. And this is how gravity arises, for instance, in 8 dimensions. But for instance, in 3 dimensions, this would be sufficient because I can get a 1 over x potential simply by summing over these kind of frequencies, 0-point energies, and get a potential out of it. But it's a different picture to think about the force because it's thinking about it as due to a quantum fluctuations, or at least to the quantum energies in a bunch of oscillators, which are describing indeed the creation, the virtual open strings that stretch between these d-branes. So this is a way of viewing gravity between d-branes in an open string channel. What's the question?
Yes, I'm not understanding now our direction. I understand that you are struggling with an important question, namely an origin for gravity, and you're engaged in this question. And now you're doing a calculation, I believe, in string theory. So is this right now string theory, or is this already your idea?
This is not my idea. What I told you in the beginning, what I'm going to do is I'm going to describe examples, and I'm going to extract the principles from them, and I'm going to formulate some principles in a moment where this will be an example of. But the principle will be more general.
So will you tell us what your idea is?
Sorry?
The question, I'm interested to know your idea of how gravity would be emergent from a different theory. So I was wondering what the idea is.
Well, okay, then let me, I think I'm almost there, but I was postponing that a little bit.
So, Erik, in some sense, this is very similar to saying that I derived the van der Waals force from the Casimir energy of electromagnetic oscillators.
Yes.
You know, you're putting something, part of the stuff in and getting part of the stuff out.
Okay. This is a way we understand how gravity emerges in a perturbative framework, which we call string theory. I think even open strings are perturbative, and they should be thought of as fluctuations on something else. So this is just a step of integrating out certain fluctuations, and they turn into gravity. But in string theory, we don't see a difference between open and closed strings very much, because we even think about them as being equivalent. So what we can do is indeed choose to describe things in open strings or in closed strings, and from string theory perspective, they're even equivalent, and this is what gives rise to ADS-CFT. But I am going to argue that there's even something underlying this, where this is indeed just a perturbative step of getting the gravity out of it. It's only the last step. There will be a step before this, but this is already telling us something about what gravity should be. It keeps track of certain degrees of freedom. And the fact that the classical closed string, so the classical equations of the closed string, describe something about the quantum properties of what I integrate out, is going to be already a hint, because I already phrased the question in the beginning. How does the classical action of gravity, namely that describes the entropy, how does it know about the phase space of the microscopic system? There's something included in gravity about the microscopic phase space. And
one lesson from this, which you haven't yet, maybe it's one of the principles, is that open strings are more important than closed strings.
There are they are indeed closer to the more fundamental framework than the closed strings. And I think this is already saying it here, because how can something classical know something about quantum? I mean, it cannot be the other way around. Clearly, this must be the more fundamental point of view.
Number two, it's the ultraviolet degrees of freedom that are the, in a sense, in this example you're describing, you can not integrate out any of the ultraviolet degrees of freedom, and indeed describe everything using open strings.
That's correct.
You don't need to close strings.
Well, this is only if there exists a limit in which we can decouple the closed string.
No. I'm just thinking about open string field theory. In a sense, contains all the closed strings.
Yes.
You never need to. You can even, it's hard to do, construct closed string observables in terms of open string fields.
Yes. Now I'm going to tell you why I think there's something even underlying open string theory. For open string theory, we also have to write down a background. We have to let them propagate on space-time.
We don't have space-time.
For open strings, we need them. And so I think open string, it's not, so I'm not going to claim that open strings is really the starting point. There must be even underlying something there, because open strings already have their own inertia. They have states that have a certain mass, and I have to already define something there. So I have to be looking at something that's underlying it. And I'm gonna do that. But this is part of the story. So there is one step in the emergence of gravity which has to do with integrating out open strings. But there's something that could even be before it. And actually, this, as I said, is perturbative string theory. Later on, actually, I reserved that for the second lecture, I will talk about M theory, because M theory is what we believe should be the non-perturbative formulation of string theory. And there we have similar ideas about how gravity emerges. However, we don't have a complete understanding of what M theory is, and I'm going to explain why we don't have it. And it's actually precisely related to this question, namely that our best guesses of what M theory is are based on an open string language. And there must be something underlying it. The other hints I'm going to take are going to come from black holes, and I'll enter that very quickly in a moment.
Can I ask a question?
Yes.
In this formulation, Newton's constant results in a way from a particular content of states.
Very good. That's correct.
But why then should it be universal?
No, sorry. It has Newton's constant captures something from the underlying description. And so it's just like Boltzmann's equation that tells the entropy is related to the size of the phase space. There's some definition of Newton's constants that counts what we have microscopically. And it's true, actually, here you can think about Newton's constants as being derived from this spectrum of states. And there is an expression that does this.
Yeah, but you start with a theory with a dimensional parameter, the tension. That's what Newton's constant as a number comes from there. The universality we're talking about comes from anything mathematical. That's the equivalent. That's built into the starting point of the theory.
Well, there's...
Why the value of Newton's constant is universal if it depends so much on the underlying theory?
No, so if you think about the way that Newton's constant, for instance, enters in the black hole entropy formula, it's clear that Newton's constant tells us something about the number of microscopic degrees of freedom. And it's a dimension full complex constant, so you should always be careful what you define here. It's the ratio of the area and Newton's constant that's really the dimensionless number, and that's going to be related to some counting of degrees of freedom. And this is also the way that it will enter in what I'm going to describe later on. And yeah, I need this. This is just answer to your question. To eventually get to need a proposal what this microscopic description will be. But I must admit there will be gaps. I mean, there are certain things I'm going to use this as part of my ingredients to get to a more general principle.
From this point of view, Newton's constant arises because the strings have tension, and if that tension is limited, the force will vanish.
Yes, but I think, okay, I think it has to do also with what is this, I already mentioned phase space. I mean, if you ask what's going on here, and this is where the general picture will come in, what actually is being done here, the position of those d-branes influence the degrees of freedom which are associated with the open strings, and they influence the phase space of it. So if you go to tensionless open strings, you're actually influencing also the phase space, and there's some way in which the volume of phase space is encoded in Newton's constant. It's a spectrum, and the fact that the spectrum has a gap in it, or at least it's a discrete spectrum, the discreteness of the spectrum is related to the tension of the string, of course. By the way, I mean, if I think about this sum and doing this calculation, I don't need an infinite sum. Because already with two terms, I can make it so that the first term cancels, and I get a 1 over x in here. And this can be used indeed to make a very tiny model of emergent gravity, basically using 1 or 2 degrees of freedom. And this is actually where what I'll mention later. There's matrix models, matrix theory, which indeed doesn't use the entire open string. It only uses very few degrees of freedom, but you can do the same calculation with the same idea of how to get gravity. So let me now come then to a more general picture. Because I mentioned string theory is one source sort of inspiration, but there's also black holes.
explain at this stage why gravity will end up attractive always?
Yeah, not at this stage, but it will be clear what it's related to. Yeah, well, I'll tell you. Okay. Let me go to the general idea. That's the idea. If you change the phase space of a certain system by changing a parameter, you change the energy levels. And you don't need to know anything else than how the phase space is influenced, because it's just adiabatic. So if there's more phase space when things are close to each other, it will be attractive. Here's more phase space because you're opening up the harmonic potential and the energy levels will go down. And now this is the basic idea, and this is actually happening in string theory, because indeed those strings which are stretched, the frequencies of them are higher when they're, so the separation is actually the set of states that I have. And now this is the picture, and this is actually what happens in string theory, and this is also what the general idea will be. It has to do with the volume of phase space. So I have to know the reason why, if matter gets closer to each other, why there's more phase space, because then I explain why there's an attractive force. So black holes tell us about is that there's a lot of phase space. Actually, let me first tell you about thermodynamics. Well, yeah. Let's see how I do this. Well, let me indeed explain this idea of the phase space, or this a little more clearly, before I get to black holes. So in thermodynamics, we have the quantity called entropy, but we also have the first law. What I'm going to do is now think about a parameter in this system which also influences the phase space. I can either take the volume, then you have something like PdV, but I also can think about a parameter which I will call x. And then you can have simply a thermodynamic force in this equation. So as I said, an example, if I think about the force as being P times the area, and I think about dV as the area times dx, if I put then PdV will be just equal to F dx. I mean, it's the same form. Because what I will explain now is an example of an emergent force, which is called an entropic force. The example is as follows. You think about a system whose entropy depends on a certain parameter, and then you can understand how a force appears. And the best most clear example is one where you have a polymer. A polymer can be thought of as some arbitrary configuration of monomers, which are sort of like little rods that can go in all directions. And when the polymer is short, there are more possibilities, because then you can have whatever. I mean, there's more ways in which these rods can point in all kinds of directions. So there's more entropy when a polymer is short. And now if you put a polymer in a heat bath, actually without having any energetic difference between this configuration and that one, there's still a force. And the reason is simply because there's an entropy change. Now it appears then, if I test this by taking an external force and pull it out, that I'm indeed changing the entropy of the system when I gradually sort of let it go back. This is not true. An entropic force is adiabatic. Namely, this is actually well known actually in for instance, DNA. You can have DNA stretched with just Hooke's law appearing, namely or in rubber actually it's the same thing. In rubber you have a polymer that creates a force, but that force is just described by Hooke's law and therefore it's conservative. And actually it's true that when you have the force acting, there's no change in entropy. Now let me explain that, how that works. So the entropy, of course, is related to the number of states. But I'm thinking about the number of states as a function of the energy and my parameter x. Now, this entropy actually is going to be an adiabatic invariant. So we're going to look at something that's adiabatic. If I then write down what the force is, you find that the force can be expressed indeed in how the entropy depends on the energy and x. So what I know now is that if I keep the energy constant and I make x, which is sort of this separation, smaller, then there's a higher entropy. But what will happen when I lower this point gradually is that instead of creating a higher entropy, the energy goes down in such a way that the entropy stays constant. If you write this out, so basically the volume of phase space is going to be constant. So what I will do is I'm thinking about E as a function of x, but I'm demanding now that ddx on this is 0. But I can write this in terms of two terms. So the force, of course, is going to be equal now to minus the derivative of the energy. And I'm claiming it's equal to the derivative of the energy where I keep S constant. So in particular, I keep the volume of phase space constant. But this I can now rewrite as follows. If I differentiate the x dependence in E, I get minus the force times, well, let me call it the SDE. And if I differentiate the x dependence here, it's actually, so this is differentiating entropy with respect to the x parameter with E constant times omega. Here I'm just using this equation and differentiate it and have two terms. And now you can see that this is actually the definition of the temperature, or 1 over the temperature. So I can rewrite this also as the temperature times the derivative of the entropy with respect to the energy, to the variable x, while I keep the energy constant. So if the entropy increases in this direction, I get a force pointing in this direction. If I would keep the energy, I mean, if the entropy increases, if I keep the energy constant. But the energy will actually go down in such a way that the entropy does stay constant. So this is just a general way of an emergent force, which has to do with just keeping track of how the entropy changes without knowing actually what the real microscopics is. We just have a way of knowing what the entropy is. So I'm claiming gravity is doing a similar thing with the entropy or the phase space of the microscopic degrees of freedom. Yeah, you can do this in a combinatorial way, simply by counting. This is a random walk. And if you take the random walk and count how many configurations you can get from one to the other, you get that this omega goes like e to the minus x squared with some constant in there. So it's indeed the logarithm of omega that starts playing the role of the potential. But the Hooke's constant depends on the temperature. If you would make the temperature 0, it would not have a force. But let me explain now the relation with this picture, because this is, I'm going to describe a related force, emergent force, which I call a reaction force. Or actually, there's an adiabatic version of that, but also a more general one. This, by the way, is the same as what I would call a Born-Oppenheimer. Force. Because, as we will see, for black holes it's very clear why there's a thermodynamic interpretation of gravity, but the other story I gave from string theory about these oscillators is much easier to understand if we think about these oscillators as some fast system. So if you have a fast system that you influence by slow system, this is actually the situation here. We have a fast system and a slow system. So the slow system is my variable x, and the fast system is the degrees of freedom that I want to integrate out. Now, if you integrate out the fast degrees of freedom and their phase space is being influenced by the slow variable, it can create a reaction force. Of course, the famous example is when you have two atomic nuclei and you have the electrons around it. I mean, then you have a fast set of variables, namely the electrons. And the reason why there is a force is because the phase space of those electrons, which are the fast variables, is influenced by the positions of those nuclei. So if there's a position x here, now the picture you get is that the phase space, why is it constant? Or how I can get it from the phase space. If I think about the energy levels of the fast variables, if the dynamics of the x variable is very slow, you can use an adiabatic approximation. That means you can solve the Schrödinger equation for the fast variables and simply look at the energies, how they behave. So these are energy levels, so En of x, as a function of x. And if I am in a certain state labeled by n, if you do it adiabatically, these eigenvalues do not cross. And that means that the number of states that I have below a certain energy level is constant. It's nice to do this in an example. If I take, which is sort of relevant for the one I did for the string. If you take a harmonic oscillator with a Hamiltonian which depends on a slow variable x, you can ask what happens to the system when I slowly vary x. I mean, it's like you have a harmonic oscillator that's going up and down. You can even do this classically and ask when I have a dial that slowly changes the frequency, what is the force that I have to apply? Here again you use an adiabatic invariant, and it's basically following from this picture. The adiabatic invariant is the quantity usually indicated by J, which is the integral of P dq. This was known actually in 18th century or 19th century physics. And of course it's related to this fact that here the quantum number n is constant, because this is exactly related to the quantum number. Because we usually write it like something like that. Now, if you think about in the phase space of P's and Q's, a harmonic oscillator has an orbit that goes like this, and then this integral is just the volume of the phase space inside. You integrate, this is the same as integrating dp wedge dq over the region in the middle. Now, more generally, I can think about this situation. Then I have a Hamiltonian. Again, with a Hamiltonian with, well, suppose I have more P's and Q's. Then I have a similar adiabatic, so this is called an adiabatic invariant. But if I have many more variables, this is not sufficient. I mean, you want to have another adiabatic invariant, or you may ask, maybe there are more integrals of this sort. But generally, this is not always possible. But from this argument, what I know is that the number of states below this energy, if the eigenvalues do not cross, stays constant. And that number of states is counted by an integral, again, of the phase space. But now I integrate over the entire phase space, say of n variables, and I restrict to the phase space where the Hamiltonian is smaller or equal than the energy E. So this is a certain part of the phase space, very similar as this picture, except that it's a much higher dimensional phase space. And this is constant. This follows from the adiabatic approximation. But it's simply purely a quantum mechanical calculation and has nothing to do with thermodynamics. Because I really think about a pure state in some quantum mechanical system that I'm slowly changing. But I get exactly the same equations because now I can write down these steps and find a similar force. So there's a certain way in which this adiabatic reaction force in the Born-Oppenheimer approximation is very similar to what I have here. Now, why is this relevant for string theory? I mean, you can think about these harmonic oscillators which I have. As I told you, a string can be thought of as sort of a bunch of harmonic oscillators. And so this kind of argument indeed has been applied. And in string theory, and I already mentioned matrix theory, we have seen gravity emerging from a Born-Oppenheimer type calculation. But the general logic now is that I can determine the size of the force not by doing a very complicated calculation in one particular system, but generally just keeping track of the volume of the phase space, because if I know this number of this quantity, I can calculate the magnitude of the force simply by a simple equation. Yes?
So what in here was the reaction force?
So what I'm going to do now is I'm going to think about this system. Well, here we know, of course, what is a reaction force, because it's simply the force between those nuclei. So you look at the system, and you ask, what does the energy do as a function of the slow variable? So I have a slow variable x and a fast variable, and then it's simply true that the slow variable receives a potential, which is the energy of the fast system in a particular state. And so if I know which state I'm in, I can sort of follow its energy as a function of n. So if I know this number, but this is the same, this information is the same basically as what I have here, because I simply keep track of how much phase space there is below that certain energy. And so there's a way in which this adiabatic argument knows about phase space. So if I think about molecular force, how that arises, one way of thinking about it is by saying that the electrons have a certain phase space volume, and that phase space volume is increasing when the two nuclei are closer, because indeed one of those electrons can go around the other, and this is why the energy can go down. So there's a general argument why there's an attractive force if the phase space increases, because this is why the energy level spacing can go down. So attractive forces have to do with an increase in phase space. So
levels can cross.
yes. So if you're not working adiabatically, then there are corrections which have to do with crossing eigenvalues. And it's quite interesting to think about that. And there's also corrections due to the fact that the motion is not slow. And they depend on the velocity. And let me mention that force. I mean, this is in a nice series of papers by Michael Berry. He studied precisely this, what's called the adiabatic reaction force. But then the correction to it is the Berry phase. There's a force due to the fact that the wave functions depend on this variable x, and wave functions generally can pick up phases when you go around some loop. And that can create a magnetic force. So then you get a gauge field, which if you take the nth state and look at this gauge connection, and you can calculate the magnetic field, and then the magnetic field will induce a force on the slow particle. You can even go further and calculate what happens to this gauge field when two eigenvalues cross. turns out that then you get a magnetic monopole in this gauge field at the point where the two cross. And actually this can be studied as follows. And I'm going to mention this because it's going to actually be relevant for string theory. How am I doing in terms of time, by the way? 10 minutes. 10 minutes. Or maybe I think I'm going to save this for then the next time. I want to actually close, since I have only 10 minutes, with some, well, okay, let me just do this. Yeah, there it is. Okay, I'll mention this. So what you do is, namely, you look at a system of two eigenvalues. I want to know what's happening to the force. I said there is a magnetic force appearing from here, with the B field just being the usual. Oh, no, sorry, I'm now getting ahead. I mean, this is more generally written by one parameter. Let me actually write down a Hamiltonian for two eigenvalues. So it's going to be a 2 by 2 matrix. And I want the two eigenvalues to cross in a certain position. So let me write actually the matrix in the following way. I think that's better. This is the same as writing just x times sigma. So I actually make the two eigenvalues to equal to be 0 when x is equal to 0. Now you can study the eigenstates of this Hamiltonian, and they indeed cross at x equals 0, but you can also calculate now the B field. And then it turns out that this is actually a Dirac monopole. And now you can even study what happens when more eigenvalues cross. And of course, you would not be surprised that in that case, the charge of the monopole would increase. And if more eigenvalues cross, you also again have degenerate states here. More eigenvalues which are the same. So if you ask what are the gauge fields that I can construct at the locations when eigenvalues cross, they're non-abelian gauge fields. So I can make from this very general framework objects which carry magnetic charge, whose on the location of those objects we have non-abelian gauge fields, where the rank of the gauge field is proportional to the magnetic charge. That's a D-brane. So there's ways in which D-branes are actually arising from a very general framework where you can think about just crossing eigenvalues. And these equations are very much used in string theory actually to describe how D-branes interact. And I think it's not a coincidence, by the way, that if I add a number here, and I look at the square of this Hamiltonian, it very much looks like the mass spectrum of a string. I want to summarize now, because I want to get back to this picture of the renormalization group and what I think. So here I'm going to summarize and actually make a statement about how gravity emerges from a more general framework. So in the quantum field theory picture, we had a Lagrangian or a theory which had degrees of freedom, operators OI, and I also introduced couplings GI. Now, the operators OI are part of what I would call the open string spectrum. Now, if I do a renormalization group flow, I integrate out degrees of freedom. Now, if I integrate out open strings, I've seen that I integrate in closed strings. There's a certain way that integrating out an open string degrees of freedom is the same as integrating in closed strings. So that means actually that I make these coupling constants, which are actually the closed strings, they have to become dynamical. But why? The reason is that if I look at the low energy variables, which are the slow variables like which are called x, if they influence the phase space of the degrees of freedom that I've integrated out, I have to keep track of that. And the reason is that it can create a reaction force. There's not always possible to integrate out degrees of freedom and just ignore them, like what's done in Wilsonian RG. The fact that if you have fast variables which are influenced by slow variables, then create a reaction force, we get to keep track of that. And that's precisely what closed strings are doing. So gravity is just a way of keeping track of the phase space volume of the degrees of freedom that I've integrated out, and therefore keeping track of the reaction forces that are being induced by those degrees of freedom. So this is why in integrating out an open string, I have to include degrees of freedom of the closed string.
Could you reformulate that in the language of irrelevant operators and relevant operators? Is that what you're doing?
No, the point is that I'm really keeping track of phase space, and this is something that is not done in Wilsonian RG. So one of the problems with Wilsonian RG is that it's never well formulated in a form where you keep track of the total phase space or the number of degrees of freedom.
Wilsonian RG, in its most precise formulation, is done in Euclidean space. What you're saying is that if you dynamically, I mean, if you think Lorentzian, then just doing at a fixed time Wilsonian RG is not enough.
There's no Hamiltonian formulation. You're telling me there's no Hamiltonian formulation of Wilsonian RG.
Or if it misses something.
I agree that Wilsonian framework has not been precisely enough formulated where you can really see that integrating out degrees of freedom gives an equivalence. But here I'm giving you a reason, namely there may be ways in which the degrees of freedom that you integrate out give rise to forces whose influence are really there at low energies, and you have to keep track of that. And the only way you need to keep track of it is by keeping track of the volume of the phase space. Sorry.
This distinction wouldn't occur if you were just doing what Wilson originally did. It's formulating Wilsonian in purely Euclidean space for a system like it. There is no then distinction.
But if we think about, I'm sure that what Wilson did has a good starting point and certain applications where you can trust it. But I think if you want to apply to the real world and say there are degrees of freedom in the UV that I can ignore, the fact we've seen already in the open-closed string duality that we have degrees of freedom in the open string sector that if I integrate them out, they can induce long-range forces. And the way they induce them, the reason they induce them has to do indeed with their phase space that's being influenced by these long-distance descriptions. And this is part of what the idea about where gravity comes from is. There is a way in which we have to improve on the Wilsonian thinking by allowing indeed coupling constants to become dynamical. And the principle that tells them then what is the dynamics is the fact that indeed the forces that are induced by the degrees of freedom that I've integrated out are indeed represented by the same variables that I have in the closed string. And then it's clear that the closed string has to know about the phase space volume, and this is also why eventually a black hole knows about the entropy of its microscopic phase space. I'll go more into that in the next lecture, but I'll leave some time now for questions. There are still some questions.
If the slow degrees of freedom remain slow, then why can't we just take care of that with the flowing of the coupling constant? Why do we need them to become dynamic? Or is that?
Because as if the no, I'm already telling you that there's a force. You can already understand the force statically. There's something putting these things together, and you want to know what's required to pull them apart. And this has to do with how the phase space changes when you change your slow variable. So So what I mean by dynamical, it means that they satisfy a certain equation of motion, but that can give rise to a static potential. I mean, like Newton's potential is just a static potential. So I'm not telling you that there must be gravitons immediately. It's something like, so I think about gravity first instance as being just a Newtonian force pulling things together. And the Newtonian force is precisely the thing that knows about the phase space. It's actually, if I want to understand gravitons, I have to even go through the things in here, because then I have to know, for instance, how terms that go like x dot squared. So I'm going to think about the leading adiabatic force, which is the one that only knows about the volume of phase space, and that you can think about as a static approximation, and this is what's called in Newton's potential.
Yes, in your toy model example of polymer yielding the spring.
Yes.
The spring has a relaxed state, and if you make it longer, you get an attractive force. If you make it shorter, you get a repulsive force. Now,
yes.
I go back to the previous question, which was why then is gravity always attractive? You never get repulsive.
So one has to understand why there is indeed always more phase space when things get close to each other. And the ultimate fate we know in gravity is gravitational collapse. And this is sort of the state of maximal entropy. And until you reach that point, there will always be more phase space appearing. So we can understand even the last bit where the increase happens by studying precisely what happens near horizons, which is something I will hope to do next time. And there we can even learn more about what is this phase space and what are the relevant degrees of freedom even. Because I will throw in string theory next time, even again, but I will need to make clear why open strings are not just sufficient. There will be more phase space. I mean, precisely to understand black holes, we have not been able to do this in open string language. We have to go to a language that's below that in order to understand the phase space of black holes. Yes?
Yeah, I'd actually answer that question differently. You haven't gotten emergent enough. Because in the end, what means, attractive repulsive means is the notion you have a distance of space near and close. And in a picture, this kind of picture, the way I look at it is that, that's the answer to that question is itself emergent. What is close and what is far is actually likely to be more. The primary concept is probably the volume of phase space.
Very good.
What you regard as close and far is simply an emergent concept. So you have to really think differently. There is no far in space. What you can easily do is count volumes of phase space. And so I wouldn't have given Erik's answer, and I'm sure upon reflection he'll change it, that if near is bigger volume, far is smaller volume, that's why it's always attractive.
Well, yeah, it's related, of course, why areas are related to the number of degrees of freedom, and the same applies there. I mean, there probably eventually we'll learn to define area by the number of degrees of freedom instead of the other way around.
It's sort of circular. Remember, space isn't primary.
But the answer I gave, I mean, it's still part of, it's rephrasing the question, namely, instead of saying why it's attractive, you're basically saying what defines the direction of the force, but
Well,
it's
so
by definition, it's the one in which it's attractive. I mean, this is.
Clearly, what we mean fundamentally, if you think about like nearness in space-time, which is connected to locality, causality, is exactly that.
Okay. Yes.
Can you quantize this force and what would be the force carriers? And especially thinking of the toy model polymer.
The polymer is purely thermodynamic, and that's a little harder. I mean, I have the other language, which is a little more closer to quantum mechanics. Here we're looking at the quantum mechanical space. So I think there are excitations that play a role here. For instance, these energy levels can have a certain spacing, and you can think about an excitation that goes from one to the other. So I believe there are excitations that we would call gravitons, but that's just like what we have in condensed matter, where we have phonons. So there could be something that is an excitation on this system playing the role of these particles. But particles for me will be excitations. They will not be the fundamental degrees of freedom in which I want to formulate what's going on. There will be something underlying that. But quantizing, I think we should not quantize gravity, we should understand where gravity comes from which quantum mechanical language. This is sort of what I think what quantum gravity eventually will be. We start from a quantum mechanical formulation without gravity, and then we see gravity appearing. And that will be in some form classical, but you can also think about this as having quantum mechanical excitations of the form of gravitons.
Yeah, but there's also an emergent effect.
That's right. It's an emergent thing then, yes. Yeah.